Hey there, have you ever stopped to think about how we actually describe motion? I mean, it seems so simple, right? Something moves from here to there. But today, we're diving into the really cool science behind it, a field called kinematics. We're going to break down exactly how you figure out where something is, where it's going, and how fast it's getting there. And the best part? We're not even going to worry about the complicated physics of why things are moving. We're just focused on the how. Ready? Let's jump in.
Okay, let's start with a quick little brain teaser to get us warmed up. Picture this. You're on a running track. You run a perfect 400-meter lap, a full circle, and you finish right back at the starting line. So here's the question. What was your total displacement? Now hold on to your answer. It might not be what you think, and it's the secret key to this whole conversation.
All right, first things first. Before we can even talk about something moving, we have to know where it is in the first place. And it turns out the answer to where is it always depends on your point of view. To actually pinpoint where something is, we need what's called a frame of reference. You can think of it like an anchor point or a starting line for all your measurements. You know, if I just point and say a cyclist is over there, that's totally useless, right? But if I say she's 100 meters east of that red building, now we're talking. The red building is our frame of reference, and suddenly her position is perfectly clear.
So to make this super clear, let's imagine a little journey. Let's say your home is our starting point. It's our frame of reference, our origin. If we were to put this on a number line, your front door is at position 0. Simple as that. Okay, we've got our starting point set at 0. Now, let's go for a walk. And as we do, we're going to unpack two of the most important, and believe me, most commonly confused, ideas in all of motion. First up, we have distance, and this is pretty much what you think it is. It's the total amount of ground you cover. The perfect example is the odometer in your car, right? It just keeps adding up the miles, no matter which direction you're going. We call distance a scalar quantity. All that means is that it's just a number. It has a size or magnitude, but no direction attached, like temperature or just plain old time. And then we have displacement. Now this is where things get really interesting. Displacement is not about the total path you took. It's simply about your change in position. It's the straight line from where you started to where you ended up. And here's the kicker. Displacement is a vector quantity. That means it has two pieces of information, a magnitude, which is how far, and a direction. So something like 5 meters to the east is a vector. A force, like a push or a pull, is another great example of a vector. So, back to our walk. You head out your front door and walk 400 meters due east to grab a coffee. Now, let's decide that east is the positive direction. So your new position is positive 400 meters. So far, so good. In this specific leg of the journey, the distance you traveled is 400 meters, and your displacement is also 400 meters. But trust me, that's about to change. Okay, this right here is the whole ball game. Let's break it down side by side. Distance is the total journey, all the ground you covered. Displacement is just how far out of place you are from where you began. Distance is a simple number. It's always positive. But displacement, well, that can be positive, negative, or even 0, all depending on which direction you went relative to your starting line. You know, the team at OpenStax puts it perfectly. The magnitude of the total displacement should not be confused with the distance traveled. It's such a common mix-up, but getting this right is absolutely crucial in physics. They're describing two totally different parts of the story of motion. All right, you've got your coffee, it's delicious, and now it's time to head home. So you turn around and you walk the exact same 400-meter path right back to your front door. And this is where the difference between distance and displacement just smacks you in the face. So first up, what was the total distance you traveled? Well, that's easy, right? It was 400 meters to the coffee shop and another 400 meters back. Your legs moved you a grand total of 800 meters. The odometer for your trip just kept on clicking up. But what about your displacement? Okay, let's think about the formula. It's your final position minus your initial position. Well, your final position is your front door, which we decided was position 0. And your initial position was also your front door, position 0. So your total displacement for that entire trip is a big fat 0. See? Pretty cool, right? Now that we've totally mastered displacement, we can build on it to understand another huge concept in motion, average velocity. This tells us, on average, how fast we were going and in what direction. And calculating average velocity is actually a really simple 3-step recipe. First, you find your total displacement. And remember, that's displacement, not distance traveled. That is so key. Second, you just measure how much time passed. And third, you divide your displacement by the time. That's it. And here's what that looks like as a formula. Average velocity is just your change in position, which we call delta x, divided by the change in time, delta t. And because this whole calculation is based on displacement, which is a vector, that means velocity is a vector too. It has both speed and direction. Okay, let's apply this to our coffee shop trip. Think about it. We already figured out that your total displacement for the entire round trip was 0, right? So if you plug a 0 into the top of that formula for average velocity, what do you get? Yep, 0. Your average velocity for the whole trip was 0 meters per second. Even though you were walking and moving the whole time, because you ended up exactly where you started, your overall velocity was 0. Wild. So you might be sitting there thinking, okay, that's a neat little physics trick, but does it actually matter? Oh, it absolutely does. This kind of precision is the language of physics and engineering. Let's look at a slightly more complicated, real-world example to see why. Let's follow a delivery driver named Jill on her route. As you can see from this table, her journey is kind of all over the place. She goes one way, backtracks, goes the other way again, and then ends up on the opposite side of where she started. It's a bit of a mess. But with our new tools, distance and displacement, we can make perfect sense of it. So when we crunch the numbers for Jill's entire trip, here's what we get. The total distance her van traveled was 3.75 kilometers, but her final displacement was negative 0.75 kilometers, which tells us she finished up west of her starting point. And because her displacement is negative, her average velocity is negative too, perfectly showing that her overall progress was in that negative direction. See how distance and displacement tell two completely different stories about her day? And this is so much more than just a classroom exercise. This precision is everything. It's how NASA engineers can program a Mars rover to land in one specific crater half a planet away. It's how a self-driving car's computer knows exactly where it is in relation to its destination. If you mix up distance and displacement in these scenarios, things go very, very wrong. Which brings us right back to where we started, with this idea of a frame of reference. We've seen that all motion is measured relative to something else, but what if that something else is moving too? Your house is sitting on a planet that's spinning, and that planet is orbiting a star that's flying through galaxy, which is also hurtling through space. It really makes you wonder, in this universe of constant, nested motion, is there anything, anywhere, that's truly standing still? Something to think about.